just a reminder, I have allowed, you can chat, so you can type in a question or a comment. You can actually unmute your microphone if you want to speak. You can go ahead and use the audio function, so you can unmute your microphone. If you're not speaking or don't have a question, please leave your microphone on mute, okay, so there's no background noise during the class. And a reminder to please be respectful and professional in all the exchange, whether it be audio or text, okay? Because whatever you say or type will be forever recorded with your name attached to it, okay? So just be mindful and respectful. Okay, so a reminder, the assignment is due on Friday, assignment number 2. Most of you look like, from the questions I've been getting, are already finished, if not finished. I noticed a lot of people have already submitted, which is good. If you're reviewing anything and you want to make changes, you could submit as many times as you like. Just remember to submit all the files again if you're going to submit. Again, if you decided you needed to make an update or a change. I'm only going to mark the last thing you submit at the deadline of Friday at midnight. Okay, I hope to get these marked over the weekend and give you feedback before you go too far down the path of assignment number 3. Assignment number 3 requires that you do some of the stuff in assignment 2 correctly, so that you have meaningful results for assignment 3. So today I want to discuss road profile design. And some of the functions in Civil 3D to input that information. So the two things, a couple things, we need to look at the standards. So I'm going to share my screen. I'm going to share my screen, and I'm going to discuss the standards from the town of Richmond Hill again. So this is the town of Richmond Hill standards. This is the document, the EPW. Engineering and Public Works Standards for the town of Richmond Hill. That's the standard I'm using for this project. We want to look under transportation, and specifically we want to look at vertical alignments, which starts right here. Okay, vertical alignments, and there's some information here. So let's look at this information and interpret the standard a little bit. So when it comes to vertical alignment, all roads shall be designed to conform to table alignment standards. So there's a table for it. Yeah, we'll look at some of that. And then there's some information here. We're going to talk about the vertical alignment, which is the road profile, the proposed road, the center line of the road that you're going to drive on. Okay. The minimum slope is 0.5%, and the maximum desirable slope is 5%. So if your road is at least 0.5% in profile and the road is maximum, 0.5%, if the maximum is 5%, you're within the standards, you can do that or anything in between. It does say here with allowable variance, you could increase the 5 to 6%, but you need permission from the Commissioner of Engineering and Public Works. So you could push it up to 6% if there's something that 5% just won't work for, and you need to make it a little steeper. But maximum is going to be within the standards, 0.5 minimum, 5% maximum. You could push it to 6 with permission. Okay, so that's what this paragraph speaks to. So on any road, the minimum is 0.5%. Okay, now on our design, and let's go to my drawing. On our road profile design, if you zoom in on your profile, okay, you will all have an intersection with an existing road. Okay, and let me just trace this. I'm going to draw endpoint, and I'm going to use layer 0. I just want to highlight something. I'm going to draw a polyline from the center here to here, and from here to here. This is the pavement. This is the center line, the crown of the road. This is the edge of asphalt. This is the edge of asphalt. And from here to here is the shoulder, and from here to here is the shoulder. Okay, so that's typical on a rural road. And then there's an embankment, either down or up or whatever's happening. But this typical shape is on everybody's profile. Okay, you're all connecting to an existing rural road, which means there's center line, edge of asphalt, edge of shoulder. Okay, and generally you're looking at approximately 2% fall on the cross section of the pavement, 6% on the shoulder. Okay, so I just want to put this into the context of what you learned in highways. So you're all dealing with this. Your road profile design starts right there at the edge of asphalt. Okay, so I want to start my vertical alignment design right there. I want to match the station and the elevation of this blue dot right here, this blue dot. That's my connection point. I don't want to rebuild any part of the existing road. So in the plan view, and this is the one I'm doing, in the plan view, my profile, this is my alignment. I'm going to keep the shoulder on this side. I'm going to keep the edge of asphalt, the center line, the edge of asphalt. So my design, I'm going to draw a line from the intersection of my design center line to the existing edge of asphalt. That's the first point. This blue dot is the first point. I'm going to design my road up to the edge of asphalt. Okay, and then from there into the site, I have some flexibility to do what I want. Okay, so that's the first point. The elevation there has to match existing, and the station value of the alignment tells you where to put it in the profile, right? So there's an alignment. It tells you there's a certain station value, right? 0 is here, so whatever this distance is to here, that's the first station. And then the elevation comes from the existing ground surface, and that's the first point on your profile, okay? So the concept, and it's for everybody, if we go to the profile, what I want to do is start, and this is a generalization. I'm going to massage the details out of this, okay? I'm going to build it up a little bit at a time and show you where you need to make some decisions. I'm just going to do this with AutoCAD. I'm just going to draw a line to illustrate what I'm saying. I'm going to draw a line from this intersection right here, and I want to go all the way to the end of the subdivision at 0.5%. Let me turn off my O-snaps. I want to go all the way uphill at 0.5%. Okay, and if it takes me out of the grid will adjust. Okay, I'm just drawing this in AutoCAD. So there's the minimum slope 0.5%. I'm just approximating it. This is the concept. Okay, you and I are in a boardroom right now. We're discussing what the design should be. This is that discussion. So here it is. For every subdivision, we're going to outlet all of our sewers. So I want to connect my storm and my sanitary to the existing maintenance holes. I want to connect my water main to the existing water main. And when it rains, if the storm sewer is full, I want my road to act like a river. If the sewers are full, if water can't get into the sewer, the road will then fill up with water in the gutter and flow. Which way is it going to flow? I want it to flow from the bulb down and out to the existing road. So everybody's concept for overland flow is from the bulb is the highest elevation, and it's going to go downhill all the way and out to the existing subdivision new intersection. Okay, so that's the concept for everybody. Doesn't matter which subdivision you have. Wherever your existing road is, you're going to come up at the minimum slope 0.5% all the way to the end of the cul-de-sac. Okay, any questions about that? And then the pipes, when we get into the pipe design, will be parallel and below the road. So they'll be just underneath the road connecting to the existing maintenance holes. Okay? But we'll worry about the servicing later. But you need to know a little bit about both. So when you talk about municipal design, there's a little bit of, it's a cyclic thing. You have to design the road profile to do your grading, to do your pipe design, to do your road profile, to do your pipe design, to do your grading, to do your road profile. It's kind of cyclical, right? So it's an iterative process. You have to kind of do something and then advance the other design and then make sure that the first thing that you did is still comparable to the details you're creating later. Okay, so a little bit of a discussion about the design process, but I need a profile so that I could put my pipes underneath it with the proper amount of cover. And then the road profile is going to dictate all of my lot grading. But if the lot grading is not working, I may have to change the profile. And if I change the profile, I might have to revisit my pipes and so on. So it's kind of like juggling jello, right? You're trying to do one thing and then it's affecting other things. But you have to start somewhere. So usually one of the first steps is design all the road profiles. Okay, we only have one. Okay, so we're learning with just one road, but certainly this applies to any subdivision. If you have 1, 2, 10, 50 roads, you want to have a sense of the road profile design throughout the subdivision. And that includes thinking about the servicing. Which way are the pipes going to flow? Which way is the overland flow going to flow? Like what if the sewers are full, how is the water going to flow on the road, and so on. So you have to have a sense of the entire concept of the design before you actually start doing the details. The focus of this course, again, is to do the detailed design based on the concept that I'm discussing with you. So really, I'm designing it, you're filling in all the details. Okay, so I'm treating you more like a junior designer, senior draftsperson. Okay, so you can draw a lot of things. You've got a lot of experience with AutoCAD, and then you have some experience with design. So I'm going to lay out what the concept of the design is. You're going to fill in all the details. Okay. And that'll generally be your role when you start working. If you get a job in municipal design with a consulting firm doing subdivision roads or any other kind of municipal design, it includes commercial properties like big box stores and parking lots and so on. The skills I'm teaching you are transferable. But the reason I use a residential subdivision, is because everything you do in a subdivision can be transferred to any other type of land development design, right? So once I cover the residential case, the other ones kind of are a simplified version of some of the tasks I'm going to teach you. So because the minimum slope is 0.5%, and this is where I want to connect, I want to come up from the existing road uphill at the minimum slope all the way to the end of the subdivision, so that when it rains, water flows to the road, the existing road. Okay. Any questions about that concept, that design concept? And if you can unmute yourself if you want to ask any questions. Okay. There's a lot more detail to come, but that's generally it. Make sure it all flows out. And then we'll get into the details. Any questions? Okay, and where did I get the 0.5%? I looked at the standard. So standard tells me it'll be 0.5%. Okay. Now, if you remember when you drew in the plan view, the edge of pavement and the back of curb and so on, remember, and let me do this again, remember the width of the pavement? How wide is the pavement, gutter to gutter? Anybody remember? What was the width of edge of pavement to edge of pavement? Or in more detail, what's the distance from gutter to gutter? That's the right of way. The asphalt, not the asphalt, the pavement. Remember the width of the pavement? Yeah, Michael, yeah, 8.5. Raymond, 8.5. So the width is 8.5. So to find the edge of asphalt, I'm going to offset, or not the edge of asphalt, the edge of pavement, I'm going to offset by half of 8.5, which is 4.25. So if you offset your center line, even if it's an alignment, it'll produce a polyline. That's generally where my edge of pavement is, right? On a typical right-of-way, if you go to the distance from the end point, if you draw a line from the street line perpendicular across the road, that's 20 meters, okay? Typical 20 meters. The only spots that aren't exactly 20 meters are the intersection, the crescent or the knuckle, and the cul-de-sac. Okay, so generally speaking, you can offset by 4.25, and then you have to go back and spend some time at the intersection, at the knuckle, at the cul-de-sac, anywhere where it's not typically 20 meters. And even on the curve, if you have a curve, from here, perpendicular to here, that's still 20 meters, even though it's on a curve, right? So I can just offset the center line 4.25 on either side, and I have my edge of pavement. Now I go back and I draw the bulb the way it needs to be drawn. I draw this bulb the way it needs to be drawn. I use my fillet command here at the intersection to get my edge of my curve. Remember, my curve is 7.5 meter radius and so on. So just like you spend time in plan at the non-standard widths, right? Wherever it's 20 meters, I'm already done. Where it's not exactly 20 meters, and the three typical cases are intersections, crescents, and cul-de-sacs, I need to go and spend a little more time there and work out those details. When it comes to profile design, those three elements, intersections, crescents, and cul-de-sacs, require attention as well because they're non-standard in terms of width. Okay, so when we look at the road profile, remember I said 0.5%, right? I can just start drawing here. I'm just doing this with AutoCAD. I will use Civil 3D in a moment. If I'm going to start here, right, that's my starting point. I'm just going to go up all the way to the end at 0.5%. And that satisfies the standard minimum 0.5% throughout. And that is acceptable anywhere you have a standard 20 meter right of way. You can do that. There are exceptions, however. Let's go back to the standard. Here are the exceptions. The minimum gutter grades for cul-de-sacs and elbows, notice they're using the word elbow here instead of crescent. So the cul-de-sac and the elbow, the minimum gutter grade has to be at least 1%. So if the main road is 0.5%, then the gutter on the cul-de-sac and the elbow has to be at least 1%. Okay, so now we're talking about two different things. This is the center line requirement, minimum 0.5%. This is the gutter requirement, 1%. So what does that mean? Let's go back to the plan view. So if the road profile, right, if I pick a point here, let me just draw a line from here, perpendicular to here, and I draw a line from here, perpendicular to here, and I go across to the gutters, and I trim, just going to trim in this zone. So arbitrarily, if I start here and I go to here, if the slope from the crown of the road to this point on the crown of the road, if from here all the way to here was 0.5% down, what would the slope be along the gutter? So if the slope from here to here is down at 0.5%, or if we go in the direction of increasing chainage, if from here we have a positive 0.5% grade, what would the slope be in the gutter from here to here? Any ideas? If the center line slope is 0.5%, what would the gutter slope be between these two positions on the road? Anybody else? Yeah, that's a more general statement, Brian. The same. Whatever the road profile is, the gutter is going to be the same, right? So if you look at the road section, I'm just going to draw something here again, right? If the profile, if we look at a standard pavement, right? If the slope here at the center line is 0.5%, then the slope in the gutter would be parallel, right? Let me see if I can draw this in 3D a little bit, right? I'm going to draw a line from here to here, from here to here, and from here to here. Okay? Kind of an isometric view. If this is 0.5%, this is going to be parallel 0.5%. This is going to be parallel 0.5%. Everybody agree with that statement? So whatever the centerline road profile is, the gutter would be the same. Okay? Now, when it comes to standard 20-meter widths, so let's look at a curve. Not everybody has a curve, but let's look at a curve. If I look at this curve, I'm going to draw an arc from the end point here to a near point here to the end point here. If I consider just this curved part of the road, okay? If the slope on this line, this curved line, is 0.5%, right? If I offset that, let me just change this to a different color so it's easy to see. I'll make it magenta. Okay, so I'm going to offset 4.25. So on this side, 4.25, on this side, 4.25. If the slope on the center is 0.5%, what's the slope on the gutter? If the slope here is 0.5%, will the slope on the gutter here be the same? Not really. It won't be the same. If this is 0.5%, right? So if the fall, think about the vertical. If the elevation here drops over this distance to this elevation here, the length of the arc is the run of the slope. The difference in elevation between this point and this point is the rise. So if you take this elevation and you subtract this elevation, that's the rise. If you divide by this length, that's the run. That's the horizontal distance. You'll get 0.5%. If you go to the gutter, you'll see that the elevation difference between this point and this point is the same as the center, right? So whatever the gutter is, I'm going to go down to the gutter. I'm going to go down to the gutter. The vertical difference between this point and this point is something, some difference. The difference in elevation between this point and this point is going to be the same. But then I'm dividing by, is this distance longer or shorter than the center line? Is the inside arc longer or shorter than the center line? The arc length is shorter. So if you take the elevation here and you take the elevation here and you subtract one from the other, you'll get the rise. If you divide by a shorter run, will this slope in the gutter be steeper or flatter than 0.5%? Will it be steeper or flatter? It's going to be steeper. And what about this one? Is this slope going to be steeper or flatter than 0.5%? It's going to be flatter. Again, the same difference in elevation. The elevation here, the elevation at the beginning, the elevation at the end, the vertical difference is the rise. The difference in elevation is the rise. The length of the gutter is the run. it's going to be flatter than 0.5%. Now, in this case here, when you're dealing with a standard 20-meter right-of-way, they'll accept the fact that if you use a minimum slope in the center line, the outside curve will be flatter, but it'll be so close to 0.5% that that's acceptable. Okay, so they allow that. So wherever you have a standard 20-meter right-of-way, if the center line slope is 0.5%, the gutter will be either a little bit steeper on the inside and a little bit flatter on the outside, and we accept that. Okay, where we won't accept it is where there's a gross difference. So for instance, I've got some sketches over here. When it comes to the cul-de-sacs and the crescents, the distance around the gutter on this bulge and the distance around the gutter on this bulge, it's not parallel. It's not like a standard right-of-way. Okay, so in this case here, they want the gutter line to be at least 1%. Okay, so we want to make the gutter 1%, which means I have to make the center line steeper or flatter than the outside turn. So if I want this slope around here, and let me draw the zone. Here's a standard 20. I'm going to draw a line from the end of this curve here, perpendicular to center. And if I extend that to the right-of-way on both sides, with respect to this line, this side is typical 20 meters wide. This is where it starts to get non-standard. And then on the other side, same thing. I'm going to draw a line from the end point of this curve, perpendicular to center, and I'm going to extend it to the right-of-way on both sides. So on this side, typical 20. On this side, typical 20. In this zone, and let me trim some stuff off. Right? First I'm going to get rid of the back of curve. We're dealing just with the gutter. Okay, so this is, if I measure the distance from here, perpendicular to here, it's 8.5, right? Gutter to gutter. If you drew this correctly, and I'm not going to demonstrate that. I want you to try and figure that out. But if you drew this correctly, you're going to have this bulge, okay? On the inside, these are actually parallel. So the gutter line here maintains its position. So if I offset 4.25 to the inside, it falls exactly where that gutter is. So this radius and this radius are parallel. They have a common center, right? They have a common center. So it's typical on the inside. Okay. On the outside, you can see it gets much wider and then comes back. So I'm going to trim off the standard stuff here, and I'm going to trim off the standard stuff here. Okay. So let's have this discussion again. If the slope from here all the way along the profile to here was 0.5%, is this gutter line slope going to be steeper or flatter? Going to be steeper. Why? Because if you take the elevation at the center line and you subtract this elevation here, right, if we're falling downhill in this direction, the difference between this elevation and this elevation is the rise. I can draw that in profile, is the rise. Right, there's a certain rise, the difference in elevation between this point and this point. And then there's the length of the center line of the road. There's the length of the center line of the road. It has a slope of 0.5%. If I look at the inside turn, the vertical difference between here and here is the same as the center line. So this rise is the same, but it's shorter. The distance along the length of this green line is shorter than this one. Shorter. So it is steeper. Everybody see that? So the rise is the difference in elevation from the beginning to the end of this cul-de-sac bulb, or this crescent bulb. And then the run, the horizontal distance, is actually this distance. It's made up of a line, a curve, and a line. Okay, same thing on center. Everybody see that? The rise is the same. On center, it's longer. This is longer than this. And you can see that here. And again, this is just an approximation, just to show you what the kind of the vertical looks like. If you look at this line, the elevation difference between this point and this point is the same as the other two, right? This rise is the same. But the run, the length of this is longer than this, longer than this. Much longer. So the slope is going to be flatter. And not only flatter than 0.5%, but significantly flatter. So when that happens, the municipality says, you know what, I don't want this to be, if you make this 0.5%, this is going to be flatter than 0.5%. But because this is so unusual, it's so wide, I want the gutter in the elbows to be at least 1%. So I'm going to go back to the standard just to remind you of that. Elbows shall be, right, the gutter in the elbow at least 1%. So if we go back to my sketch, I'm just trying to give you a visualization. Okay, if this length, this green line here, if the length, that's the run. If I want the vertical difference from here to be 1%, if this was 1%, what would the slope on the center line be? Flatter or steeper than 1%? If I made this exactly 1%, which is this slope, would the center line slope be flatter or steeper than 1? Same rise, shorter run. Is this steeper or flatter than this? It's going to be steeper. So when you're designing your road profile, in the case of an elbow, you have to design the gutter so that it's at least 1%, which dictates what the slope on the center line needs to be as a minimum. So if I make this 0.5%, this is going to be flatter than 0.5%. If I make this 1%, this is going to be flatter than 1%. Still no good. I need to kind of reverse engineer it. I need to guarantee this is 1% by making this one on center steeper than 1%. And that's the trick. And this is a technique I call the when the dog wags the tail. I have to design the profile so that the gutter works in the end. So I'm going to start with, if this was 1%, what should this profile slope be? If this was 1%, what should this slope be? Okay, and it's a pretty quick calculation. I'll show you. Okay, so I'm going to do a little bit of hand sketching. I'm going to go to my overhead camera. Okay, does everybody understand the problem? In this area, right, where the standard 20 ends and then begins again, right? So this is the zone. This is the, between this station and this station, I have a center line that has to guarantee a minimum gutter grade of at least 1%. So I'm going to reverse engineer it. I'm going to fix this at 1% and calculate what should this profile be. If this is exactly 1%, what should this be? That's the question. Okay, and this is something you all need to calculate. Now, the nice thing is with AutoCAD, you can get the length of the run, right? This is a polyline. If I list it, it'll tell me how long it is. So that's the run. And if I list this one, it'll tell me the run. That's the total length from beginning to end. And same thing here. So if you use a polyline, you can get the run of the triangle. Then we can calculate the rise based on 1%, right? So I know the run comes from the drawing. I know the slope. I can calculate the rise. Okay, so let me go to my sketch. I'm going to do this overhead camera stuff. So let me see if I can draw this again. So if I have a gutter that does this, so here's the center line. Line, there's a curve, there's a line. That's the center line. On the outside, it's going to curve away. It's going to curve away, and then it's got a curve that connects them. So that has a certain length. That's the gutter line. Okay, what's the length of the gutter line? Let me get the lengths. Let me go back to the drawing. So what's the length of this line? I'm going to list this. The total length of the polyline tells me how long the gutter is. 52,372. 52,372. 52.372. And what's the length of the center line? 36,890. 36.890. Okay, back to my sketch. Okay, so this is, let me draw it a little bit better. 52.372. It's a little easier to read, sorry. And 36.89. Okay. So that's the length of the gutter where the bulge starts and the bulge ends, right? And then we still have the center line of the gutter on this side. We don't worry about this gutter. Okay, we're not going to worry about this gutter. It's the one on the outside that dictates. So if I know the length of this gutter, I'm going to draw that run. There's the length, 52.372. And then I'm going to draw this triangle. The run here is 36, so 36.890. If I need this to be minimum 1%, right? I want that to be 1%, then this slope has to be 1%. Okay, so I'm just trying to relate what you see in plan to kind of a profile, right? 90 degrees. I know the run. I know the slope. What's this rise? If the run is 52.372 and it's 1%, what's the rise of this triangle? You have your calculators? Anybody else want to confirm that? Right. So the rise would be 0.524 if you're going to work to 3 decimal places. Okay. Now, the difference in elevation from this point to this point, the rise is this height here. The difference between the center elevation and the center elevation at this point is the same. Okay, you have to recognize that the difference in slope in elevation between here and here is the same as it is between here and here. So this rise is also 0.524. What's the slope on the center line? And give it to me to 3 decimal places. What's the slope of this? So I know the run, and this is the trick. This has to equal this. That's the whole point. So what's the slope of the center line? Okay, and this is a calculation you're all going to have to perform. You're going to get this length and this length from your particular crescent, right? It's going to be different than mine. Everybody has a different geometry there. So we take 0.524 divided by 36.890 equals times 100, and we get a percent grade of 1.420%. Okay? So if I design my profile between this point and this point at 1.42%, that guarantees that the gutter slope is at 1%. Everybody agree with that statement? If you don't understand why that's true, then now's the time to figure that out. Okay? And then the other thing you'll notice, the distance from here to here on the inside gutter is going to be shorter than 36, but the rise is the same. So this gutter is going to be steeper than 1.42. It's going to be greater than 1.42. So this takes care of itself because it's shorter. So when you're doing an elbow, assume that the gutter on the outside is 1%. You have to calculate what the center line gradient is going to be. So if I design the profile between this station and this station at 1.42, that guarantees that the gutter will be at least 1%. Okay? Now 1.42, and there's more decimal places, it's kind of a weird number. It's not a non-standard number. When we're designing road profiles, we'd like to pick a nice clean number to work with. And typically we use multiples of 0.5 or 0.25%. So I would round this up. I'm going to make this a little bit steeper. So the next closest value is going to be, you know what, just call it 1.5. If I make this steeper than 142, what will the slope on the gutter be? Will it be steeper or flatter than 1%? Will the gutter on the outside be steeper or flatter than 1%? Anybody else? It's going to be steeper. So if I make this 1.5%, if I make this steeper, this is a bad drawing, let me redraw it, right? Whatever this slope is, right, 142. If I make it steeper, 1.5, then the rise gets bigger. This will be the same rise, and then this gets steeper than 1%. So I start with a calculation. Make this exactly 1%. Figure out what this slope needs to be, and then round it up a little bit. Round to this multiple, either a quarter or a 0.5% of a percent. So I'm going to round it up to 1.5. If I make the center line a little bit steeper than 142, that guarantees the gutter is going to be a little bit steeper than 1%. And now my design on the center line is nice and clean. I have a nice clean number to work with. Okay? And that's traditionally the design you do in profile. You get to choose your slopes. Make them nice, clean numbers to deal with, right? The gradients should all be a multiple of a quarter or a 0.5%. That's kind of a traditional notation, okay? 142 exactly will give you 1% exactly, right? But we don't have, remember, this is a minimum. So I'm going to do a nice clean design on the center line. I'm just going to make it steeper, call it 1.5, and then that guarantees this is bigger than 1%. Okay, any questions about that? Okay, how you input all this into the system is going to be a different calculation. So when you go to your once you draw, and this is here's another example of why you have to correct any mistakes that might happen on the previous assignment. If we go back to AutoCAD, if you draw this correctly, and you draw this correctly, you can get the length, the run, right, the distance. You can get the run from the drawing, right? But if these are drawn incorrectly, then this entire calculation is going to have to be revisited. Okay, so that's how you design the profile on center so that you guarantee a minimum gutter grade on the outside of the elbow at 1%. Okay? Next semester, you're going to deal with elbows again. In Milton, you have to perform this calculation again. You must design the center line to guarantee a minimum gutter grade on the outside. Okay, and I'll do a review next semester, but I expect you to be able to do it already, right? So you should practice this calculation and determine what you need. Okay, there will be a way of checking later when we do the actual model of the profile, but that'll come when we do our input. Any questions about the elbow? Okay, so this calculation here, take the time to make sure you figure out what your centerline slope should be in the zone where the elbow is to guarantee a gutter grade of 1%. Okay? All right, so that's one thing, the elbow. Professor, is our elbow length also? No, it's going to be different. It depends on the angle, right? So the angle between this center line, this line here, right? This line and this line might be different than mine. So you're going to get slightly different lengths for the center and the elbow. They'll be close, but they'll be a little bit. Yeah. So everybody has to do their own, right? May not be exactly right. I'm giving you the process, and I'm giving you an example with hard numbers, but it's just the concept, right? Whatever length you have for the outside gutter line, whatever length you have for the center line on your particular subdivision, that's what you have to use. Yeah, good question. Okay, so I'm just giving you the generic process. So that's the cul-de-sac. That's the elbow, the crescent. The crescent has a similar calculation. It's a little bit different, but it's a similar concept. Okay, so let's go through that one. So it has a similar problem. Let's think about this. If the slope, and let me find where the non-standard width starts, right? So here, I'm going to get rid of my gutter, my back of curb. So I'm dealing again with the edge of asphalt, right? The distance from here, perpendicular to here, is exactly 8.5. And when does that stop? Well, it stops from this point to this point. That's the last time you have a standard 20-meter right-of-way, right? So this is a typical 20 down here, and then it starts to kind of morph. It widens into this bulb, right? So if we trim this off, right, that's typical 20. How do you deal with this? Okay, now, the profile design is along this geometry. That's the profile of the road. The gutter is this green line. That's the gutter, okay? And I want it all to flow from here out, right? So the elevation is going to be high here, and then downhill in this direction. And then from here along the gutter, downhill in this direction. Okay? Now, in this particular case, it is symmetrical. So I'm going to work with just half of this drawing. It's exactly the same on the other half. So I'm going to trim from center the gutter on one side. So the length of this that I just erased is going to be the same on both sides. It's symmetrical, right? So if I list this, I have a length of 57,445, undo. And if I trim it on the other side, this gutter length is also 57,445, right? So it doesn't matter whether you use the left or the right, it's symmetrical. This is the simplest case when it's symmetrical. It's not always symmetrical, but in this case it is, right? So let's deal with this, and then eventually you'll be able to deal with anything, okay? So what I want, let me trim it. I want this slope along this gutter to be exactly 1%. What's the slope on the center line supposed to be? Now this one's a little trickier because we're not dealing with a center to edge of asphalt relationship that's the same. Remember here, from the center to the gutter is a standard width. from the center to the gutter is a standard width, right? So the difference in elevation between this point and this point, vertical, remember the rise is the same on this location and this location. That's not true here, okay? Remember, this is the edge of the gutter, right? The pavement, it's the gutter line. Where would the edge of asphalt be, right? What's the offset to the edge of asphalt on the inside? Anybody remember? Think about the intersection you designed. How far is it from the gutter line to the edge of asphalt? Yeah, okay, Samuel, that's the back of curb. Warren, you have it right. So if I offset by 0.3, here's where the asphalt is supposed to be. So that's the last point on the asphalt. So I'm going to trim off my center line right here. And I'm going to delete this. So this gap is 0.1 meters. This is the length on the asphalt of the center line. That's the profile I need to design. This is the length of the gutter from that point all the way out to the edge. Okay? So now the difference between these 2 points is different. The vertical difference is different than the vertical difference here. So it's a little bit more complicated than what we did here, right? Here we're going from the center to the edge of pavement, standard width. From the center to the edge of pavement, standard width. Here we're doing something a little different. We're going from the center to standard width, and then from the center down to the gutter. The difference here vertically is different than the difference here vertically. So it's a little more complicated, but the idea is going to be the same. I need to know if this run is 1%, this shorter run on center is going to yield something steeper than 1%. What is that number? That's what I have to try and calculate. So let's do this with some actual hard numbers. I'm going to put some elevations to it, and it'll be easier to see. Okay, so let's go back to my sketch. I'm going to do a hand sketch again. So I'm going to keep this drawing in mind. And if I go back to my overhead camera, when I'm drawing my cul-de-sac, I have my, and I'm going to exaggerate this, right? So where the typical 20 meters stops, right? There's your standard 20. Where your typical standard 20 stops. There's a center line that goes all the way to the edge of asphalt, and then you drop down into the gutter, a width of 0.3, and then that bulges and comes around and ends up here. So you have a typical width here. What's this dimension? What's the distance from here to here? Think about the offset in a typical right-of-way. How do you get from the center line to the edge of pavement? What's the offset? Yeah, 4.25, yeah, 4.25. And what's this gap here? Everybody remember what offset we used? 0.3, so this is 0.3. Now this 4.25 takes you from the center line of the road to the gutter point. Remember this? Right? Takes you from the center to the gutter point. That is the 4.25. Okay? But it's made up of parts. What's the slope of the asphalt pavement? Now you have to go back to the standard. Go back to the standard, which is here. Remember page 164, I believe. What's the slope on the, we're using RB2, right? What's the slope on the asphalt? 2%, so this is 2%. Let's go back and look at the details of a curb and gutter. So now you need to look at OPSD 600. I'm not going to worry about the slope, but if you're at the edge of asphalt, right, and you're going to go over 300 millimeters or 0.3 meters from the edge of asphalt to the gutter point, what's the vertical difference? What's the rise from the edge of asphalt point to the gutter point? Anybody see that on this drawing? Yeah, it's right there, 25 millimeters. So if you're at the edge of asphalt and you go to the gutter, you fall down 0.025 or 25 millimeters, or in English, 1 inch. Okay, so let's go back to my drawing, my sketch. So if you fall from here to here, 0.025 meters. Okay, and I got that from the curb and gutter. Okay, so now if the distance from here to here is 4.25, what's the distance from crown to edge of asphalt? What's this distance? First of all, what's this distance? What's this distance here? from here to here? 0.3 meters. So what's the distance from here to here? What's the asphalt width? 3.95. Okay, everybody see that? Okay. If you don't understand where these numbers are coming from, and notice I'm pulling it from different sources, right? I know the width of this number 4.25 came from the cross section. How do I know? Because this is 8.5, and then we're going to take half of it to get to the gutter. Then I have to look at this standard. Well, the width is 300, so what's left over? 0.3 from 325 is 395. Okay, so that's where these numbers are coming from. So I'm compiling a sketch with information from various sources, and that's part of your job, right? What's this? What's that? What do I need to know? Okay. So I want to look at, from the center line, what's the vertical difference from the center line down to the gutter point? What's this height? Get out your calculators. What's this vertical distance in meters, 3 decimal places? Trung, okay. Anybody else? 3 decimal places, Samuel. I'm going to work to the millimeter. Not quite. I'm going to go down 2%, 395. So I'm going to take 3.95 times 0.02. And that's the difference from here to here. And then I'm going to add this piece here. So I'm going to add 0.025. So the vertical difference is going to be 0.104. 0.104. Okay, in meters. Let me draw that a little more. A little bigger, 0.104 meters. Okay. Yeah. Okay. So how do you get from here to here vertically? You go down 0.104. Okay. How do you get from here to here down from the edge of asphalt to the gutter? 0.25. Okay. So keep these numbers in mind when we're about to do this calculation. What I need from the drawing now is the length of the center line and the length of the gutter line. How long is the gutter? How long is the center line? So let's go back to the drawing. So I'm going to list this polyline. It's going to tell me the total length, 57.445, 57.445, and I'm going to list the center line. Remember, I trimmed it, right? It's 0.3 meters short here, right? Because this is where the asphalt ends. So I'm going to list this, and it's 46.191, 46.191. And let me go back to my sketch, 46.191. Go back to my camera. So this is 46.191 from here to here. And this is 57.445 from this point all the way to this point. Do we have to trim that center line on assignment? No, you did not. No. I'm doing this on the side. So that's a good question. When I do this, when I'm doing these calculations, I'm going to make a copy of the bulb, and I'm going to make a copy of the crescent over to the side, and then I can do my work. Okay, but don't disturb the design. I'm just trying to get some information from this geometry, right? So I make a copy of these two things, like I did here, and then I try and work out the information I need. So don't disturb the drawing. You're just trying to pull some information off of that geometry. Good question, Michael. Do it off to the side. And I would keep this in the drawing. No one's ever going to see it, but at least you have a record of where your numbers are coming from. What I'm doing here, I would do on paper, right? This is a record. I would keep this in the file for the project so that if anybody asks me, hey, what did you do? How did you do it? I have a record of all the numbers I used for my calculations. Okay? So now let's look at this information. Let's draw the profile from the gutter at the top to the gutter down at the bottom. Okay? So the length of that line is here. So I'm going to draw it down here. So there's the run, 57.445. Okay, I want it to be 1%. 1%. What's the rise? Calculate the rise. I know the run. I know the length. What's the rise going to be if the slope is exactly 1%? So you take 57.445 and you multiply by 0.01, and you get exactly, to 3 decimal places, 0.574. 574. Okay? Any questions about that? Everybody with me? So that's the vertical difference between this point at the top of the gutter and this point at the bottom, right? It's going to flow in this direction at 1%. Now, I need to figure out what the rise is on the center line. I know the run, I need the rise. Okay, so the rise now is not 57.574. Okay, it's going to be different. Okay, first of all, if I knew, let's do it with hard numbers. If this was elevation 100, if this was elevation 100 at the top of the gutter, what would the elevation at the bottom be? No, we're falling downhill. You have to subtract, Warren. Yep. So this elevation would be 99.426. Okay, everybody understand how we did that? Okay. What would the elevation here be if I come from the gutter up to the edge of asphalt right here? What would this elevation be at the center line? What's this elevation at the top of the center line here? 100.025. Yeah, I would take the gutter elevation 100 and add 25 millimeters or 0.25. Everybody with me? Okay. How do I get from the gutter to the center line of the road? How do I get from the gutter up to the center line of the road? What am I going to add to this number to get this number? And what's that elevation? So I'm going to take this elevation in the gutter and I'm going to add 104. So take 426 and add 104. So 426 plus 104, 99,530. Yep. So this is 99.530. Everybody with me? If there's any confusion, now's the time, because this is a critical calculation. So now I know the elevation at the beginning, at the top of the center line profile, and I know the elevation at the end where the bulb ends and I have my standard 20-meter right-of-way. The difference between these two elevations is the rise of this profile, right? So what's the difference between this number and this number? What's the rise? So 100.025 subtract 99.530. The rise is 495. I get 495 if you round everything. So if I look at the profile of the center line, I know the run, 46.191. I now know the rise, 495, 0.495, and now I can calculate the slope. Okay, bad drawing. Let me just write that again. 0.495. I know it's hard to see up there. Let me draw it somewhere else. It's a little bit fuzzy on screen. Draw it somewhere else. So I know that the run is 46,191. Let me see if I can do it here. The run is 46.191. The rise we just calculated is 0. Whoops, it's off screen. Sorry. 0.495. We can calculate the slope. 3 decimal places. What's the slope? 0.495 divided by 46.191 equals times 100. Give me percent grade. 1072, right? Yeah, so this is 1.072%. Okay? So this is the calculus. It's very similar to the last one, except the vertical difference is not the same, right? To come up to the from the gutter to the center line of the road, that's a different vertical difference than you have here, right? When you're going around the elbow, the difference is the same. So the rise is always the same. Here, it's a little bit different. So now I know the slope from here to here has to be at least 1.072% so that I get it exactly 1% on the gutter. Okay. Now this is a funny number to deal with. So we want to round it up to the nearest quarter or half%. So what I would do here is I say, you know what, let's just round it up 1.25. If I make the center line steeper, this is going to be greater than 1%. Okay. So now I'm going to design my road center line at 1.25 from here to here, and that'll guarantee that the gutter is going to be a little bit steeper than 1%. Okay? So like the expression I used before, this tail is wagging the dog. I'm designing the dog, but you have to consider what the tail is going to do when you design that center line, right? You have to design the center line. You have to design the center line to guarantee the gutter requirement. And that's true in all cul-de-sacs, and that's true in all elbows. Where you have your standard 20, it's fine. Whatever you do on the center line, the gutter is going to be parallel on both sides. It's going to be close enough. But with these large deviations in width on a cul-de-sac or a crescent, you have to go through these calculations. Most municipalities have a center line minimum grade of 0.5% and a gutter grade of greater than 0.5%. In Richmond Hill, it's 1%. You'll see next semester in Milton, it's I think 0.75%. So they always exaggerate it a little bit to guarantee you have flow. Water must flow in the gutter, and 0.5% on the gutter because of its flat nature is always a little bit challenging. You don't want standing water, otherwise you're going to get ponding and hydroplaning in the summer months, and then it could end up with ice in the winter. So that's the procedure. I know it's a little bit complicated. We're using a combination of rise over run equals slope. But the distance and plan is coming from stuff you draw in AutoCAD. Nothing Civil 3D here. I'm just leveraging AutoCAD a little bit to get my lengths and my runs. Okay, any questions about this procedure? Okay, so now at this station, all the way to this station, I know what slope to use. And if I go to my elbow, from the beginning of the elbow, let me just draw a quick sketch here. From the beginning of my elbow, right? From the beginning of my elbow, and this is the center, right? From the beginning of my elbow to the end of my elbow zone, I know what slope to use here. So this has to be, in my case, at least 1.5. At the crescent, I'm going to use 1.25 at the cul-de-sac. And everywhere in between, where I have a standard 20, I'm going to use 0.5%. So on a typical width, 0.5% everywhere. When you go through a knuckle, I'm going to use 1.5. When I go at the end of the cul-de-sac, I'm going to use 1.25. And that will guarantee the minimum gutter on those unusually wide spots. Can you please repeat how you got 99,426? 99,426. Where's 99,426? This one? This? Stephen? You want to know where this number came from? Yeah. So I have to start with a number. I'm going to assume the elevation here is 100. And then I'm going to go downhill all the way to here at 1%. So I know the run. I know the length. I got that from AutoCAD, right? The length of the green line is right here, 57,445. I want this to be exactly 1%. So here it is. If the slope is 1%, and I know the run, calculate the rise. So that's the vertical difference if you go from here downhill to here. So if that's the rise, I take 100, subtract, right? If this is elevation 100, I'm going to subtract this distance vertical, and then the elevation at the other end, which is this point here, is 99.426. That make sense? All right? Remember, the distance from here to here in the profile or the side view is the distance along the gutter line. So that's the run. I can calculate the rise, right? 1% of the run is the rise. I know the elevation here, I'm assuming, is 100. I'm going to subtract the rise to get the elevation at the other end, which is this point here. Okay, yeah, good. This is the time to work this out. This is a very typical standard calculation. What changes from project to project is the length. The geometry is different in plan, so the center line length and the gutter line length all changes, right? But you need those two distances. And typically, if you draw them correctly in AutoCAD, you can get it pretty quick, the length of the polylines. And then you go through this analysis. Rise over run equals slope. I have the run, I have the slope, what's the rise? Now I can use that rise somewhere else, figure out a new slope, and so on. Okay? So this procedure is a very typical calculation when you're designing cul-de-sacs and crescent. Okay? All right. So I'm going to erase this, and I'm going to draw a sketch of what the design should be, okay? Very quickly. And then I'll show you how to input it into AutoCAD. Or into Civil 3D, rather. So remember, we have the existing profile, we have the pavement, and we have the shoulder. And then your existing ground might come down like mine. It might come down and then back up. It might go up. It could be, depends which topo you're using. So it doesn't matter what's happening inside the subdivision. Everybody is dealing with the existing crown and the two edges of pavement and then two shoulders. That's typical. Everybody's got this shape. The design, remember I said, all the way to the end of the subdivision is going to start here and go up at 0.5%. Oops. Let's try this. I'm going to start here. I want to respect that elevation, and I'm going to go up at 0.5%. But where this beginning, remember the elbow? The elbow looks like this. It comes around and comes down here and down here, remember? At this station and at this station, between these two stations, which we're going to identify in plan, there's two stations where 0.5% is not going to work. I need to make it steeper. And in my case, I calculated 1.5. So I'm going to do this again. That's no good. This is no good. Between here and here, I want to go 1.5%. And then all the way to the end, it's standard 20 meters, I can go 0.5% again, 0.5. And then when I get to the entrance of the cul-de-sac, from here all the way to here, wherever this station is and wherever this station is, I want to go 1.25%. Okay? So we start at the existing edge of asphalt. We go where it's a standard 20 meter wide, I can use 0.5%. Then to go around this area here, I need at least 1.5. So this station begins, this station ends, where I need 1.5. Then standard 20 meter right of way, I can go at 0.5%. And then from that point up to the end, I need to go 125. So what's this station? What's this station? Then go up steep. So when you look at that, it looks kind of funny. Why not just use 0.5%? Well, right here we have an elbow. And over here we have a cul-de-sac. Okay, so 1.25. So that's basically the design. You need to confirm this. Make sure you know what these numbers should be. Round them up a little bit, right? 0.25% or 0.5%. Always round up so that you guarantee you have at least 1% along this gutter and 1% along this gutter. Okay, and that's almost the whole story. There's one more thing to discuss, but that's generally the design. Any questions about that? Okay, now one last thing to look at with the standard. If we zoom in here, what's the slope here? What would the design slope be on the tangent? What's the slope on the pavement, approximately? What's a standard tangent slope? 2%, right. And from the center line, it's going to be minus 2%, if you think about it in profile, right? We're going downhill. This one is actually positive, going uphill, right? So we're going to come down, I'm going to blow this up. I'm going to go down at 2%, -2, and then at the edge of asphalt, at this point here, I'm going to go up positive 0.5%. This is the profile. What's the A value? You remember highways? What's the change in slope? The change in slope? 2.5. That's A, right? The change in slope, right? We're going from -2. We're going to add 2.5 to get to positive 0.5. Everybody with me? Nightmares from highways. Okay, everybody remember that? Let's go back to standards. There's a note about this. If I was teaching this in class, this is when I walk to the door and stand right near the door so nobody runs away. Okay, so let's go back to the standards. Whoops, not that one, this one. So if we go back to the standard that speaks to, I forget where it was now, let me go back to my bookmarks. If I go back to here and we talk about vertical alignment, vertical alignment, here we go. So the minimum slope is going to be 0.5%. Okay, and this project, we're not going to get anywhere near the maximum. So don't even worry about it, 5%. It's 0.5% with these exceptions, right? Minimum gutter grade of 1% on the cul-de-sacs and the elbows. Good. Here's the other note. If you have a grade change of more than 1.5%, you need a vertical curve. So let's go back to the drawing. If A is equal to 1.5 or greater, you need a vertical curve. I have 2.5. I'm supposed to put a vertical curve here. That's what the standard says. Okay? I don't want to do that. If I do that, then I'm going to be reconstructing part of the asphalt. Okay? I don't want to disturb the existing pavement, right? I don't want to disturb the existing pavement. I want to match this point here. If I put a vertical curve in, then it's going to destroy part of the existing road, and I don't want to do that. So here's the trick at the intersection. Okay? This is the scenario. If you're connecting to a tangent, everybody understand the problem? Any questions about what I'm dealing with? And I'll show you how to deal with it now. But that's the problem. If I have an A value bigger than 1.5, I need to put a vertical curve in. Well, I don't want to put a vertical curve in. So how am I going to fix this? Okay, so this is what I'm going to do. If you're connecting to a tangent, right? If you're connecting to a tangent and you're coming down at 2%, what we're going to do is take that asphalt edge. I'm going to come down at 0.5% for a little bit, and then I'm going to go up at positive 0.5%. So instead of starting here at 0.5%, right? Instead of starting here at 0.5%, bad drawing, right? Instead of starting right at the edge of asphalt, because the difference between positive 0.5 and -2, the change in grade here is 2.5. What's the change in grade here between -2 and -0.5? What's the A value here? 1.5. Do I need a vertical curve? No. As long as I'm less than 1. If it's greater than 1.5, you need a vertical curve. I have exactly 1.5, I don't need a vertical curve. If this is -0.5 and this is +0.5, what's the A value here? 1. That's also less than 1.5. So instead of starting my design here and then having to deal with a vertical curve, I'm going to take that existing slope, match that point, come down at 0.5% over a certain distance, and we'll discuss what that needs to be. There's a minimum distance here. And then once I get to this low point, there's a low point in the road, right? Low point here. Then from there, I'm going to come up at 0.5%. Now I have 1.5% grade change, a 1% grade change, no vertical curve, no vertical curve. And that's the trick. Okay? So I'm just looking at the standard and finding a creative way of avoiding putting a vertical curve in. And this is typical. When a slope wants to come down, you typically don't match the edge of asphalt. You come down below it and then come up to it gently so that the 2 points here have a grade change of less than 1%. And that's a standard practice in our industry. You show up to work with that little bit of knowledge in your back pocket, you're going to go a long way. Okay? That's a typical way of dealing with falling toward an existing road and avoiding a vertical curve. And it's done all the time. Okay, so now let's look at the design again. I'm going to draft it one more time. So if my existing pavement looks like this, right, with the shoulders, I'm going to match this point here, right? I'm going to come down at 0.5%, 0.5%, and if positive change is increasing in this direction, this is going to be a negative slope. Then I'm going to come up at 0.5%, positive 0.5%. Then that's where my cul-de-sac starts. I'm going to go steeper, 1.5 to the end of the crescent, right? So that's the crescent zone. Then I'm going to go on a typical 0.5%. These are all positive. When I get to the entrance of the cul-de-sac, I'm going to go up to the end at 1.25%. And that's my design. Negative 0.5, positive 0.5. 1.5 through the elbow, 0.5 on a standard 20, and then 1.25 on the cul-de-sac. And And that's generally it for everybody. What's going to be different from person to person? Where you put these station values and the distance between them, right? It's going to vary, right? These points in the plan are going to be different depending on which subdivision you're working on. But that's generally the design. Everybody will have 1, 2, 3, 4, 5 tangents with those slopes. The length is going to vary from subdivision to subdivision, but those are the slopes. The trick is, what's this station value? 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 You need to know the stations so that you can type in the slopes. You remember when you go to a profile, you're going to get that table, and the first 2 columns are station elevation, right? But then you can type in the grade. Remember grade in and grade out, right? There's a couple of columns here with a grade in and grade out. I'll show you how to use those, okay? So the next step is to go to Civil 3D, but this is the design. This is the concept for everybody to follow. That's what your profile should look like. What's going to vary are the station values, right? How far apart these things are, depending on which subdivision you're working on. Depending on which topo you got, what elevations you're going to have. But at a glance, they'll all look like this. If there's a very small section of straight road between elbow and bulb, is it practical to just continue the grade? Sometimes it is, but don't do that. Try and keep it as low as possible, right? So what you're saying is if this distance, if this gap is very, very small, can I just start my 1.5 and go all the way to the end? That's practical. You can do that, but please don't. I recommend you don't do that. We're trying to get to the end of the subdivision as low as possible. So taking advantage of 0.5% when you can, so that you can have the lowest elevation possible at the end of the site is what we're trying to achieve. Okay, so you know, there's reasons why you do or don't do that. Okay, right now I'm telling you don't do that. Right, so on the straightaways where you have a standard 20, use 0.5%. Right, but through the elbow and the cul-de-sac you can use the steeper values. Any questions about the concept? Okay, this is kind of a boardroom discussion, right? We're starting this project. How are we going to do it? This is what I want you to design. Now you can go to Civil 3D and actually input the design. Okay, and that's what I want to show you next. And the next part of the lecture is really just sit back and watch, so you get a preview of what you need to do, and then you can go ahead and practice it. You can review the video, and then you can review the procedure. Okay, if you try and do what I'm about to show you, you might miss something. So my suggestion is sit back, fold your arms, and watch, okay? And watch what I do and understand what it is you need to do, okay? When I'm teaching you something, it's important you understand what you're doing and why. How to do it, you can always learn that anytime, right? But what and why is more important. Should we wait for our assignment to come back before doing it? No, you can proceed to do your assignment 3. You can start doing this even if you don't know the results. If you have to make changes, then you can always adjust this design later, right? So if it turns out that like let's say the station values, you design them here, they're supposed to be further apart, maybe you messed up, you can always fix that later, okay? So you don't have to throw anything away. You have to make an adjustment for sure, but you can at least proceed, okay? I'll talk about that when I do it, okay? But I wouldn't wait because it's good practice. Then if you get it right, you're good to go. If you didn't, it's a minor adjustment. All right, so let's go to Civil 3D and identify these things. The first thing we want to look at is where is this low point station, right? And what you're going to see as a general theme is there's places in the plan that dictate where you put things in the profile. Okay, let me show you with the cul-de-sac and the elbow. So let's go back to the drawing. So I'm going to go back to my drawing. Let me get rid of some of the stuff here. Okay, so in order to do this, you have to draw your edge of pavement, your gutter line. You need that drafted everywhere. Okay, I didn't do mine, but I will. I'll show you a couple things. So where's the last place I have a cul-de-sac? Well, I think it's right here on the right of way, from here to here. There's my standard 20, and then it gets wider. Okay, so there's where my cul-de-sac starts. Right? So everything above this line is standard 20 meters wide. Everything down in this area is the cul-de-sac. So there's the entrance to the cul-de-sac right there. Right? That's the first point on the cul-de-sac. The elbow, not quite, but there is a point where the elbow comes out, comes back, and so on. So I'm just going to temporarily draw something. Again, I don't want to give away the geometry, right? So somewhere over here, I don't know where, it depends on where you drew it, is the last time you have a standard 20-meter right-of-way. Like somewhere, and then it gets wider. I didn't draw it, right? So somewhere between here, and let me draw another one here. Okay, so you drew a bulge here. Okay, I'm not going to draw it. I don't want to show that to you. I want you to try it. So somewhere between here and here is where the pavement gets wider on the outside. Okay, so that's the beginning and that's the end. So you need to know where this station is. Again, this is not where yours is. This is just an example. So that's the last, so from the station value, that's the last time you have a typical 20. Then you go around the curve, and that's the last time you have a non-standard. Then you're back to the typical 20, and so on. So you need to identify these points in the plan as station values in the profile. Now, there's a couple of ways of doing it. You could draw a line from the intersection of this label to the intersection of where that happens, right? List that line, right? 1865 and add it to 60, so it's 60, 1865. You could do that, right? But I'm not going to get lost in the numbers. There's better procedures. So here's the procedure. Again, I'm just guessing where these zones are, right? You'll know exactly after you draw them. So if we'll go back to my sketch here, right? You have to draw exactly where your standard 20 ends, right? Here's my 20 meters standard width, right? That's the last time I have a standard 20, and this is the first time my standard 20 comes back, right? So if you draw this correctly, then you'll know exactly where this station and this station is in the plan view, okay? And I don't want to give it away. So I'm just going to guess, right? You'll have 2 points. This is the last time you have a typical 20, and this is the first time you have a typical 20 back. In between here and here is what I call the zone, the elbow, okay? So if I want to find that station value, here's a handy tool. I'm going to draw a point, AutoCAD point, P-O-I-N-T, point. This is AutoCAD. And I'm going to snap to that intersection, center line, and that point where the zone starts. So there's an AutoCAD point. Draw another one at the other side. Right? This is the end, intersection. And there's another AutoCAD point. Now, if this point is hard to see, there's two commands you want to explore. One of them is called PD mode. PD mode. This is all AutoCAD, PD mode. Right now I have it set to 2. If I change it to 3, watch what happens to what the point looks like. It's like an AutoCAD style. It looks like an X. If I put number 2, it looks like a cross. If I put number 6, no, not 6. If I use 2, 5, no, sorry, 3, 5, it looks like a cross with a circle in it. It's just the style for the AutoCAD point. So if you don't see anything, PD mode, I would change it, PD mode, I would change it to either 2 or 3. Right, a cross or an X. If you still can't see it, then there's the size, PD size, and change it to something a little bit bigger, right? So 0, you're not going to see anything necessarily. Actually, 0 is, if you regen the screen, it's always the same size, so don't use 0. Give it an absolute number. So change the PD size to either 2 or 3. 3, 5 changes the size. 6, 4. Right? So PD mode, I would suggest using a 2 or a 3. And then PD size, I would suggest anything bigger than 2 or 3. So you can change and manipulate the size and the style of the AutoCAD point. That's not Civil 3D. So put a point where you know the zone starts and ends, right? And then there's another 2 over here, right? I'm going to have a point here, intersection, and I'm going to have another point here, right? And it's going to be, I'm just going to guess, somewhere there's an edge of asphalt here, right? It's going to be here, but offset 0.3, and you put your point there, and then you don't need that line anymore, right? You just want to show the gutter line, not the asphalt point, right? So again, my points, these 4 points I just drew, I'm just guessing. You'll know where those points are after you draw all this geometry correctly, based on the standard for an elbow and a crescent, elbow and a cul-de-sac. Okay, this is just for demonstration purposes. Once you identify in plan where those zones begin and end, right? So this is the last time we have a standard 20. This is the first time we have a standard 20 back. And then from here all the way to here, in my case, I'm going to design my profile at 0.5%. And then from here to here, I'm going to design it at 125, right? So 0.5%, 1.5, 0.5%, 1.25, just like the sketch, right? I'm identifying where I start and end my elbow and where I start and end my cul-de-sac. Okay, so if I want to draw those points from the plan view to the profile, there's a handy tool for it. So if you click on it, right, 1, 2, I'm going to do all 4 at once. You can do one at a time. It's up to you. So I'm going to do all 4 at once. So if I know these points are in the plan, I want to identify them in the profile. I'm going to go to, so I've selected them. You can see the blue dots, right? I've selected them. I go to my profile. So under Home tab, I go to my profile view. And there's a command called project points to profile view. So once they're selected, you start this function and you go over to your profile and you touch the grid. So I'm going to touch the grid and then it's going to give you this dialog box. Now those points in the plan are AutoCAD points and I snapped to locations where the elevation is 0. See, the elevations are all 0. If I say okay, so this is what not to do. Watch what happens if I say okay. Look at my grid. See how big it got? Because my design is up at 100 and something, but those points are at elevation 0. So now I've got these points way down here and my kind of design range elevations is way up here. So don't do that. Here's a trick. Let's do this again. Same function. I'm going to do something a little smarter. So I'm going to go back to here. Choose the points. These are the points I want to project to my profile. I'm going to start the profile project objects to profile view. I'm going to pick the grid. And instead of accepting those zeros, I'm going to go to elevation options, select all, and temporarily I'm going to say, you know what, get your elevations from the existing ground. They'll be close to my surface, right? Elevation from existing ground. And now it changes the elevation. So instead of 0, which is what's in the plan, it's going to get the station values from the alignment, but it's going to get the elevations from the existing ground. So watch what happens now. They're all in range, and they should all be kind of touching the existing ground. And then you don't get that huge grid that I just showed. Okay, so I'm going to delete this and this. Okay, so there are the zones for the beginning and the end of the elbow and the beginning and the end of the sack. Right, so everybody needs to do this. The elevations are wrong, but the stations are correct. Okay, the last thing we need to do now is this thing. Remember this trick? Whoops, this trick here. I want to start here. I want to go down and then up. I need to know where this station is. I also need to know where this station is, but this one is critical. Here's the trick. Again, I'm going to draw something very, very crudely. So if I had a polyline from, so if you drew your arcs correctly here, remember, draw your arc here, 7.5. You use the fillet command. You remember this? Right? If you finished your intersection design, if you had finished your intersection design, right, I'm just going to draw a line. So if this was touching, oops. And if this circle was touching, okay, I'm just trying to create some geometry. This is wrong, but I just want to show you something that would look like what you did. Okay, so if you did your intersection design, these curves would exist, right? And this would be broken here. Okay, so forget what's happening here. You're going to have a curve. Your gutter line comes and then it curves away. Your gutter line comes and then it curves away. Because you're existing, right, this is not exact. Again, it's an approximation. Once these are drafted correctly, mine are not. They are not perfect. Yours should be exactly where they're supposed to be, okay, based on the discussion we had last week. Once you draw these two, these points are not going to be exactly across the street from each other, right? If I draw a line from this endpoint, perpendicular to center, and if I draw a line from this endpoint, perpendicular to center, they're not going to be exactly across the street from each other. Why? Because the existing edge of asphalt is not an exact line. It's a bunch of points connected in sequence, right? The low point wants to be, of these two ends, of these two curve ends, the one that's closest to the inside of the subdivision. So not this one, this one. That's my low point station right here, the one further in. The only time these are directly across the street from each other is if you're designing a road at 90 degrees to a new road. So two new roads at 90 degrees, these will be exactly across the street from each other. But when you're dealing with an exact road and maybe the angle between this center line and this center line are not exactly 90 degrees, then you're always going to get a bit of a shift. Okay? It's not going to be perfect. Of the two, the one closer to the inside of the subdivision, the one furthest away from the intersection dictates. So you want to put a point right there. Okay? Now it's hard to see if you don't draw those two lines. So what I do is I put a point in at these ends, put another point here, and I project these two. When I project these two, it'll actually figure out the station value perpendicular to center. Okay? So at a glance in plan, you can't tell which is further away from the intersection. I know it's this one. But if I put the point here and here, not on the center line, watch what happens when I project it. So I'm going to project both. Enter. I'm going to go to the grid view, somewhere near the intersection. And again, the elevation is 0, so I'm going to say temporarily put it on the existing ground, because it's really the station I'm after. Say OK. And now, if you look at the profile, you'll see, oh, this one is further away from the intersection than this one, so I'm going to throw this one away. That's my station for the low point. It's easier to see in profile. If you just project both, you can quickly see here which one is further away. It doesn't matter which side of the road, whichever one is furthest away. If you want to draw the two lines that I had before, right? If you want to draw a line from this endpoint perpendicular to center, or this endpoint perpendicular to center, if you want to draw these and decide, yeah, it's this one, I won't even worry about that, and then just project the one, you can do that, right? But that's a lot more work, right? So to avoid drawing these two lines, I just project both of these into the profile, and then you can, at a glance in the profile, see, oh yeah, this one's too close to the intersection, ignore it. That's my station for the low point. So now I have the station for this position right here, the low point. And then I need the edge of asphalt here. You can either get it from the profile, it's right there, or you can project it. You can actually put a point on center. Point at the intersection of the edge of asphalt and the center line. That's my first design elevation. To match existing, project that point, and it shouldn't be a surprise that it falls exactly here. Click here, change this, get your elevation from the existing ground surface. When I say OK, it should land right here. There's my first point. So there's the station. 1, 2, 3, 4, 5, 6 station values. Elevations are garbage. 1, 2, 3, 4, 5, 6 station values. If you use this technique, you never get lost in the numbers. I don't have to write down a station value. I don't have to, remember what the elevation, just points in the plan and project them to the profile. And now you have all the design stations. The elevations are wrong, but you have all the design stations. And that's the technique I expect you to use. So again, if you draw any of this wrong on assignment 2, it's going to put these points in the wrong spot in the profile. Okay? So again, you can proceed. And then if you do have an error with this, if you make a mistake here, then you can always adjust these. Just, oh, I drew this in the wrong spot, right? It turned out that this was actually over here. Well, just put a point over here. And watch this. If I move this point in the plan view, it actually moves it in the profile view because it's projected. It's dynamically linked. So if you have to redraw the elbow, just keep this point that if you decide to start now. Once you move this, watch that. Let me put it way over here. Right now it's way over here. And if I move it back, it'll be closer to here. It's dynamically linked because it's constantly projecting. Right? And that moves it closer. So if you do make a mistake on your gutter line, you can just project the point to the new position and then adjust your profile. I'll show you how to do that. Does everybody understand this technique of projection? Okay, it's a really simple tool, And you don't have to remember the number of the station or the elevation of the surface. You just you draw stuff, you're using geometry, and you're leveraging the function to take a point and plan and show you where it is in the profile. Very simple tool. Okay? And we're going to use that tool many, many times, but this is one of them. Now we go back to something you did in highways. In highways, you put in a profile. Remember in highways? I'll give you some more nightmares. Remember in highways, you had an existing ground that looked something like this. It was kind of low, high in the middle, and then back down. And then you went uphill, uphill, downhill, downhill, and you put in vertical curves. You remember this? When you drew that green profile, that's what we have to do next. Okay, but it looks like this blue line. So here's how you do that. Okay, so we're going to go to Profile, Create by Layout. This is a bit of review from highways, Create by Layout. You're going to pick the grid. I want to do my design in here. I'm going to give it a name. I use the repeat street X, that's the horizontal street name, and then I say Finish Ground, FG. When I say OK, I get this dialog box. You might recognize this from highways. And then it's not the first button, but the second button. And now you want to set your O snaps before you start. Set your O snap to clear all node, because all those points are nodes. Say OK. And now I'm just going to connect the dots, starting at the low chainage, 0, and work my way upstream, up chainage, from low chainage to high chainage. So I'm going to use this second button, PVI, and I'm going to snap from this node to this node, to this node, to this node, to this node, to this node. Okay? And there's my profile. The stations are what I want. The elevations are garbage. So how do I design it? I go back to this table. You might recognize this from highways as well, Profile Grid. And you'll see the list of station elevation, station elevation, station elevation. The stations are all correct. The elevations are all wrong. They're existing. I need to propose them. So then I work in this grade out column. And I put in the slopes. Start at the beginning and work your way to the end. So what's the first slope supposed to be? Anybody remember? What's my profile? Negative 0.5. So, and you can actually, this is dynamic. As I change the numbers, it's going to redraw. Right? So watch here. So this one here should be negative 0.5. So there's my low point right there. What's the next one? Positive 0.5, so you don't need the plus sign, so 0.5. So there's my first stretch, 0.5% up to where the elbow starts. Then the slope in the elbow, if you remember, the slope in the elbow, right there. Go back to the grid. The slope in the elbow is positive 1.5. And notice the grid is adjusting because I'm adding data that's higher than the limit that I had before. Then from there, I go all the way to the entrance to the cul-de-sac at the minimum slope, 0.5%, 0.5. And then from there, I go to the end of the cul-de-sac at 1.25. Remember the design, right? 1.25. And that's my design. Now the negative sign doesn't show up, but it is downhill. Negative 0.5. Positive 0.5, positive 1.5, positive 0.5, positive 1.25. If I design the center at 1.5, my gutter is going to be at least 1%. If I design the center at 1.25, my gutter in the cul-de-sac will be at least 1%. So when you look at this at a glance, you might be wondering, what was this designer thinking? Why is he not using 0.5% everywhere? Like, why change the slope at these locations? Why are these locations critical? Why are they key? Why are they using that PVI location? Why are these stations where they are? The station values in the design profile are actually key locations in the plan, where your elbows, where your cul-de-sacs, and where your intersection low points are. So the points in the plan dictate the location of your profile points, station values. The elevations now are taken care of. If I go back to that grid, right? If I change the slope, it's actually updating the elevation. So the proposed station elevation, station elevation, station elevation, the elevations are changing when I change the slope. So as I update the slope, I'm updating the elevation, right? So if I change this to 2%, the last number is going to go up, right? So it's adjusting the slope as we go. That's the design profile. This is the first step in assignment 3. There's a lot more to do in assignment 3, but this is the first step. So if you can get this done for next week, I know you're working on your assignment. Some of you are done, so that's why I want to introduce this now. Or if you hand it in on Friday and you got nothing to do on the weekend, you can start doing this. Okay? So you have to have assignment 1 done. You need the edge of pavement. You got to know your bulb and your crescent location. Then draw those points in the plan, project them to the profile, connect the dots with the profile design using this tool here, and then go to the grid and change the slopes based on this design concept. This is the concept. All of you will use these same numbers, but you'll have different station locations, different elevations, depending on which site, which topo you were assigned. But at a glance, they'll all look the same. That's your homework for next week. If you can get that done for next Tuesday, when I see you next, then we can proceed to cross-section. We're going to look at the assembly with sub-assemblies, and then we're going to build a corridor. And the corridor is the most critical piece of information to do your grading design and the most critical piece of information to do your servicing design, right? And you'll see why when we get to it. But you can't build a corridor without a plan, your alignment, your profile, the vertical design, and a cross-section, which I'll discuss next week. I don't want to put any more on you today. Any questions about this procedure? It doesn't take long to do. It took me longer to explain what you're doing and why than actually how to do it, okay? So I hope you understood what I was talking about, and then you can review the video to see how to do this. There is no PDF for what I just did, okay? And all the hand calculations we did, right? This is board work. I would have done this on the board. I would have asked you to stop looking at your computer and watch what I'm going to do in terms of the engineering design. The minimum slope. How did I get this 1.5? How did I get this 1.25? Those calculations. Review the video. Okay, there's no PDFs for anything I did in class today. The points in the plan, you can delete them. There's 2 schools of thought. You can delete them. And again, if you delete them, if I delete them in plan, if I delete these 2 points in the plan, they disappear in the profile, which is fine. So you can delete them, or you can put them on a layer and freeze them. They shouldn't be visible. They're a technique, a tool for you to draw this profile, right? So in the profile, you don't want to see them. So if you don't delete them from the plan view, you certainly want to delete them from the profile view. Right? And then the mystery gets even bigger, right? Why are those PVI stations and elevations where they are, right? So when you look at this, if you didn't come to today's class, right? Why is that station elevation there? Why is this one here and not over here, right? Or why is that not over here? And why are the slopes what they are? Okay, and that was today's discussion. The station value is dictated by the plan location of those key points, and then the profile slopes are coming from minimum and minimum to guarantee gutter slopes here and here. And then this little trick at the intersection, right, where you have a little bit of a low point, right? Come down half, come up at 0.5%. So you can avoid using a vertical curve. Most of what you do is in the atypical things. What happens on your standard right-of-way, right? What happens in here is very quick. What happens between here and here is very quick. Just like you spending time in the crescent and the cul-de-sac and the intersection in your plan view, you're going to spend time in your profile at the intersection, at the elbow, and at the cul-de-sac. What happens between those atypical things is pretty quick, pretty standard stuff, right? Because when you get stuff that are atypical in width that you have to spend a little more time on. So Stephen, the answer to your question is I don't want to see those points. So either delete them or freeze them. They're only there for the purpose of the technique. That's the short answer. Any other questions? Okay, so that's it for today. Please review the video. There's only 25 of you in class. If you know your classmates that aren't here, the other 15, tell them to review the video. It should be available late today or tomorrow. And it explains everything again. It goes through the calculation, and then it shows you the civil 3D technique. The civil 3D part of this lecture is very, very short and quick. The explanation of the design is really the focus of today's class. Okay. Once you know what the design should be, then you can input it pretty quick. So to get to this stage before next week is going to be fast. Are you going to update our grade and grades? Yeah, I'll for assignment 1, right, Sumitra? I'll post it, right? But you all have your email results, right? Everybody knows how you did on your assignment, but I will put it on gradebook. Yeah, thanks for the reminder. I'll try and get that done today. Okay, that's it for today. I'll see you next week. You too, Michael. Thank you. Everybody's shy. Nobody wants to talk. Eh? You all had an opportunity to turn your microphone on, but nobody did. All right, I'll talk to you next week. Your microphone's not working. Okay. Carl, you don't like your voice. All right. So if you want to type, that's fine, right? But I will respond verbally. So that's good. Okay. Have a good rest of your day. Bye-bye.